And this is defined as, in order to define XA, I need to first define a reference state. Remember in thermodynamics, you always have a reference state? So here I need a reference state. So in order to define it, I'm going to need a reference state, which I'm going to signify with a sub-zero. Whenever I use a sub-zero, I mean a reference state. And that reference state is going to be, for example, NA0, NB0, etc., T0, P0. If I happen to have a situation, what do we call it, V0. If I have a non-isothermal system, my reference state will have a T0 in it. If I have a non-constant density system, my reference state will have a V0. But in the simple case where I have constant density and isothermal, it's just a bunch of concentrations. In this case, mole numbers. Constant density, it's equivalent to concentrations. And then the fractional conversion is the conversion relative to the reference state. Now, in many cases, it's convenient. You can choose a reference state to be anything you like. In many situations, it's convenient to take the initial condition as the reference state. But sometimes you have situations where that's not the most convenient choice. So for example, if I have a steady state reactor, it doesn't care what the initial condition was. It forgot the initial condition already. So that's not necessarily a convenient choice. And you'll see there are, in different situations, there's usually an obvious convenient choice for the reference state. But, so from now on, I'm always going to use a sub-zero for the reference state. And when I want to talk about initial condition, I'm always going to write it this way, parentheses 0. Unless I define the initial condition to be the reference state. Okay, so what is XA? Once I have a reference state, it's defined as, when I write a colon equal, that means the definition. It's equal to NA0 minus NA of T divided by NA0. So it's NA0 is the reference state. NA of T is how much I have now. So NA0 minus NA of T is how much NA I've used up since the reference state, divided by the amount in the reference state. So it's the fraction of the reference state that I've used up. In an imaginary experiment where I somehow started at the reference state. It doesn't have to be the experiment that I did in that imaginary. So you can see that NA of T is, I can use NA of T or XA of T interchangeably, whichever one I find more convenient. Okay, so let's just notice NA0 XA is equal to NA0 minus NA of T. NA0 minus NA of T is how much A I've used up. So NA0 XA is how much A I used up. And if I solve for NA of T is equal to NA0 minus NA0 XA, 1 minus XA. And that's the A I have left. So it's just another variable. It's no big deal. And notice, if I want to write CA, if the system is constant density, then this is just, I divide both sides by VA, and I have CA0, 1 minus XA. So I have a simple conversion between X's and C's. Okay, so let's redo some of the algebra we just did, but let's do it in terms of XA, in terms of CA. No big deal, it's equivalent. So for example, let's do first order. In the first order reactions, we say that RA is KCA minus KCA. Minus KCA0, 1 minus XA. So I just converted, where I saw CA, I put in a CA0, 1 minus XA. And I also need a DCA. So if this is CA, then DCA. So if this is CA, what is DCA? What was I up to? Higher mathematics.
Minus dx.
Anything else?
Minus CA naught dx.
Minus CA naught dx. Remember, if I go around the room and ask you a question, don't be scared, because that means it's a really easy question. If it's not really, so don't be afraid to answer. If it's not really easy, I'll ask for a volunteer. That's how you can gauge the difficulty of the question. Volunteer, you got to think about it. If I point to you, it's really easy, so it's no harder than saying your name. Okay, so let's plug into here. So I have into this expression. So dCA has just turned into CA0 dXA with a minus sign. That's dCA over F2, well, that's whatever's left. So I've got minus everything but the K. So I've got another minus CA0, 1 minus XA. And that's equal to KT. Okay, let's notice a couple things. First, the minus signs cancel. And of course, I have to dXA. This goes from XA of 0 to XA of t. Now, I'm going to notice a couple things. So the first thing is the minuses cancel. Next thing, what else cancels here? Front row. I guess I'm up to you. Omar? What else cancels?
The CA naught.
CA naught cancels. This is a first order reaction, remember. And notice the CA naught cancels. There's no CA naught left in the problem. As it will turn out, that only happens for first order reactions. For no other reactions, but only first order reactions. And that's a very nice property of first order systems. Okay, the next thing to notice is I put in an XA of 0 and an XA of t. If I happen to choose, if it happens to be convenient, to choose the initial state as my reference state, let's see what would happen. If my initial state is my reference state, then XA of 0 is NA0 minus NA of 0 over NA0. If NA0 equals to NA of 0, what is XA of 0? 0. So often, in your book, most books, I don't know any book that actually clarifies this distinction, just implicitly, whenever it's convenient, assumes that the initial state is the reference state without making it clear that that's a choice. And that's not always the best choice. But so we're going to make that choice when necessary, when it's convenient, but we're going to say we're making that choice. We're not going to leave it understood. So here I'm allowing that not to be the choice. It might not be. And now I want to integrate dx over 1 minus x. Because I have 2x. What is the integral dx over 1 minus x? Higher mathematics. I don't know.
The line of 1 minus 6a.
You missing something?
Yeah.
Minus. So use the minus to flip the limits. So xa of t to xa of 2. So this says I have the log of 1 minus xa of 0 over 1 minus xa of t is equal to kt. You want me to write it smaller so it would be harder to see? Log 1 minus xa of 0 over 1 minus xa of t is equal to kt. Now, so here's the answer in terms of xa, and I want to show you that it's equivalent to the other answer. So to show you that it's equivalent, I'm going to use pink chalk, because whenever I use pink chalk, it's magic, and it's equivalent. If I multiply top and bottom by CA0, and then look at this formula, I can see this is just equal to the log of CA of 0 over CA of t, which is in fact the exact same expression I had over here. So it's equivalent. It has to be equivalent. Yes.
So then why is it more convenient than writing it this way?
For this expression, this
Oh,
reaction, it's not more convenient. Sometimes it's more convenient. So why don't I do an example where it might be slightly more convenient? Since you asked, I'll do another one. Let's see. Yeah. Okay, let's do another example where it might be slightly more convenient. So let's assume I have A plus B goes to products. And let's assume this is elementary. Then RA, what's RA here if it's elementary?